I do a lot of work in foundation engineering, in situ soil tests, and I've gotten interested in scour. And I do a lot of work in infrastructure performance, do a lot of testing. So just a little bit of background about me. You don't see me like a stuffy professor in the office. I'm out in the field. I have a dirty hard hat, and I try to work hard myself. Just to remind you what I do as a professor, try to break the ice a little bit, is what my friends think I do, that I teach classes all day. And my family thinks that I invent things and do all these wonderful things as a professor. Society thinks I get the summers off by the beach and get to just kick back all the time. My students really, this is what they think of me, especially when I give 2 tests next week and about the end of the semester. And this is what I like to think I am, Indiana Jones, and how exciting this job is. But really what I do is chase money. That's what this job is about, trying to find the next research dollars. But nonetheless, that's just to break the ice. What we're going to cover today is what I understand from Sarah is that everyone, pretty much, or most everyone has taken civil engineering undergraduate courses, and most everyone's had that basic soil mechanics course. And what this is going to be is I'm taking the soil mechanics course that I teach, and we're condensing it down into a 2-hour review. That means we have quite a bit of ground to cover, from soil type, soil classification, the old moisture volume mass relationships, and I'll talk a little bit about compaction, stress in a soil mass, water and soil, permeability, just the basics of that. Talk about consolidation and shear strength and compressibility, which hopefully are the building blocks that you're going to need for the presentations that Robert and John are going to give you subsequently. I've got a lot of slides here. There's a lot of material to cover, so you may think that I'm kind of pushing you. I'm going to go pretty fast, but we'll have a few breaks in here and there for you to give me some feedback, and also maybe work a little problem or two as we can, maybe together. So sit back, relax. If you have any questions, again, contact Sarah or chat with Robert, and if we need to stop for a minute, raise your hand, and hopefully we can get to that question. And then, of course, you'll have this information to take a look at once this is all complete. So let's go ahead and get rolling here. So the first thing I want to talk about is, in terms of geotechnical engineering, we start talking about soil types. And under soil types, we're going to talk about soil types, rocks, and then clays are kind of special in terms of soil. So we want to cover the mineralogy of clay a little bit so we understand why clay behaves the way clay behaves. So again, this is where I usually start out in my undergraduate courses. So soil, when we're looking at it as an engineering material, is a 3-phase material. And if you look at the figure on the top, if I just took soil and put it in a container, it would be an amass of air, water, and solid particles. And I try to make that delineation. I don't just say air, water, and soil, because soil is a mixture of air, water, and solids. So when I start talking about soils, then we're looking at the air, the water, and then the solid particles are the material that's inside. So where do those solid particles come from? Well, they come from rock usually. They start out as rock. And we have 3 potential parent rock materials out there. We have igneous rock, which was rock that was cooled from lava or magma, and then we have metamorphic rock, which is rock that has changed over time. It could have been an igneous rock, it could have been a sedimentary rock that changed because of heat or pressure or some plastic flow in a geologic time scale. And then sedimentary rocks probably were soil before they became rock, and it was just basically sediments that were deposited over time, and over a geologic time scale, they cemented together and got harder, and maybe there were more sediments that sat on top of them, and it created a consolidated sediment, which would become a rock. And again, so it could actually change and become something else. But these rocks are the source of the particles that we have in soil. Now, the rocks that contain quartz are going to break down into sands and gravels. So quartz-containing rocks are going to be sands and gravels. And rocks that are composed of calcium, magnesium, and or sodium break down into clay minerals or clay soils. There's a distinction that heavily, there's a lot of quartz in the Earth's crust, so that quartz is going to break out into sand particles and gravels, and then where the calcium, magnesium, and sodium are, we're going to get clay particles from it. So moving on from rocks to soils, in generality, we can talk about some soil formations that we have. And we have two broad categories of soil formations. The first broad category is alluvial soils, or sorry, transported soils. Inside of transported soils, we have several possibilities. Alluvial soils is one. You see that top figure on the left. I'm going to grab my pointer here, and so you see that the top figure on the left, we have alluvial soils, and it's just a delta. And I chose a delta because it shows that as alluvial soils are deposited, once we go from where the water is coursing through the valley to where it spits out in the lake, we have a deposition environment where once the velocity of the water changes, the larger particles are dropping out, but we still have some finer particles out here in the pond. So what's happening with these transported soils, talking about alluvial soils, we're getting sorted particles, sorting of particles. Glaciation moved a lot of soil, it still moves a lot of soil today. And glaciers, as that ice moves very slowly, is plowing soil under and making moraines. It's pushing and plowing soil, and that's causing some sorting of soil and movement of soil. Windblown soils, or loess, is a very, typically in geotechnical applications, is a really bad thing to find, because when that windblown soil is deposited, you get a very honeycombed and unstable soil mass. So loess or windblown soils are a type of transported soil. And the other thing, it's kind of odd to consider it that way, but a landfill is a transported soil. We're transporting a bunch of garbage and putting it in a hole, and we're covering it up with soil, and we're putting more garbage and covering it with soil. We have these alternating layers of garbage and soil. So thousands of years, when the next civilizations are excavating our history, they're going to find these places and these weird transported soils that we've created in landfills. But the broad thing is, it's soil that has moved from one place to the next, either when it was soil or when it was weathered as rock and dropped off somewhere else. And one of the hallmarks of a transported soil is we get a lot of sorting of particles. So you're going to get larger particles in a group somewhere, maybe in a layer, and then smaller particles may be deposited when the water got slower and slower. So the sorted particles is the important aspect of it. Then that brings us to the next kind of soil formation is residual soils. And so if the other type was transported, then this type of soil is residual. It means it's where it resides. It went from rock to soil with never being moved. And you can see the picture I have right here on the left. This is one of my graduate students holding a big chunk of residual soil. It looks like a rock. It looks like it has rock, it has the grain structure of rock, the crystal structure. But if you begin to crumple it up, then you get what he's got in his palm of his hand, where their grains look like sand and possibly silt in his hand. So this residual soil looks like the rock. It can have some of the parent rock structure, but it's soil. And one of the things about residual soil is the particles are not sorted. With the transported soils, we had particles that were sorted, like sands were sorted and clays were sorted. You can have a mass of different soil particles together in these residual soils. So they're going to be a little bit different than the textbook soils that we tend to study. Our geotechnical texts, whatever you studied in the past, and really even the information I'm going to present today, is really we usually assume that we have one type of particle, sand, clay, whatever. In terms of residual soils, we can have quite a bit of mixture, and that can be a design challenge, which becomes a much more advanced topic as far as the mechanics of that. Probably the most prominent zone for residual soil in the United States is the Piedmont. It runs from up in New Jersey all the way down to where we are in Auburn, Alabama. It's pretty much on the tip of the Piedmont. It runs pretty much the I-85 corridor through the United States, I-85. So among
Hey, Robert, can I interrupt real quick? I mean, Brian.
Yes.
I'm so sorry. A few people are having a hard time hearing you at certain points, so I'm going to risk sounding like an English teacher right now and ask you if you could slow down and enunciate just a little bit more for us.
Okay, that's no problem. But,
thank you so much.
Yeah, thanks for letting me know. I'll slow down just a little bit. In terms of those soils, then, thinking about what the grains, how can we define the grain types? And this is where we're drilling down to really look at the individual soils themselves. So looking at the grain types in those transported or residual soils, we have gravels, sands, and silts, which are just more or less particles of that parent rock that have been disintegrated. So you can think about a gravel as just being a little rock. Sand is a little tiny rock, and silt is even smaller rock. But clays are a different beast altogether. They're formed from the decomposition of rock into some secondary minerals. So something then happens, a chemical type change happens to the original minerals, and they form new minerals. And so clays have a fundamentally different behavior in general than sand, silts, and gravels. I'm going to mention organics here for once and then leave it alone. Organics are sometimes treated like soils, but they have organic matter. They're a very different animal altogether. And the one thing that I would say about organics, typically in geotechnical applications, are a bad thing. They tend to decompose. They tend to lose volume, have a lot of compression, and they typically have no strength. So that we typically avoid them at all costs. So that's pretty much the discussion we'll have on organics. So gravels are particles or rocks that are between about 8 inches and 0.2 of an inch in dimension. They're bulky particles, which means that the length to width is about the same, or in a reasonable number. So there's an angular gravel on the left, probably a young gravel that's just been broken up from a larger rock mass, and then more of a rounded gravel on the right, which is something that's been transported a lot. It's probably been in a river. So you get the transported aspect. So an angular versus a rounded type particle. We can have the same thing for sands. Sands are much smaller, 0.2 of an inch down to 0.0003 inches, which is really about down to the last particle size that you can really see. And I'm probably be challenged to see anything that small, but you're getting down below what you can see with your naked eye. So those are your sands, and again, sands can be angular, and they could also be angular like the one up here, and they could be more rounded. And they may not just be the typical beach sand that you've seen. They may be made up of different sand particles, different minerals, different kinds of silica, different colors, but nonetheless, that's the same particle size. Silts then would be the same type of sand particles, just smaller. So here's an electron micrograph of a silt, and it looks very similar to the sand particles we saw before. It just is a whole lot smaller. And then here's a neat picture of the silt on someone's finger in water. So you can see the silt kind of holding onto that water and resting on a finger. So you can see how fine the particles of that silt are. Oh, yeah. Let me use that. Yeah. So on the left, you got the micrograph. On the right, you can see that the silt particles being just very small. And silt has a little bit of affinity for water, and it has some similarity to clay, but then fundamentally we're going to learn how to determine the difference between the two. Now moving on to clays. Clays are very different. They're down in the same size range as silts, but their particles are no longer bulky. These are plate-like particles. They're on the left, this is a kaolinite particle. And I love this picture because it really shows how platy these particles are. They're very thin with respect to their length and width. Now on the right, we have a montmorillonite particle that's even thinner with respect to its length and width. So they're very, very thin, and they end up having an affinity for water because of this thinness and the electrochemical properties. And we're going to see that here in the next slide. So clay minerals are a little different than the disintegrated rock that silts, sands, and gravel are. Clays are made up of some basic minerals, and these minerals are stacked together to make the clay minerals. And the way they're stacked together and the way they're shaped and the electrical charges that they have kind of give clay that affinity for water. So you think about a clay mineral is made up of these, let me turn my pointer here, made up of these two basic building blocks. So the first thing is the alumina the silica tetrahedron right here. The silica tetrahedron is the one on the top. You have a silicon ion in the middle. You have 4 oxygen ions around that. Make a little tiny pyramid. And what they do is they kind of link together by sharing the oxygens and create these chains and create sheets of this silica tetrahedron. The other basic building block is the alumina octahedron. You have kind of a double pyramid here with aluminum ion in the middle and oxygen ions around the edge. And then they kind of lay on their side and stack together and make a more complicated network even than the silica tetrahedrons. Now what happens is you're going to get groupings of positive and negative ions. So you've got a positive ion in the middle and a negative ion on the outside of the oxygen. Same thing with these guys. And the face of these sheets become electrically polarized. Now, we'll look at the next page, and it may help us understand that. So if you look at the clay minerals, if you think about that aluminum octahedron and silica tetrahedron, so here's an alumina octahedral sheet in the kaolinite and a silica tetrahedron. The kaolinite is just stacks of aluminum and silicon together, and they just stack up, and electrically they bond to one another. With the morillonite, you have a sandwich of silicon, aluminum, and silicon, so the silicon tetrahedron and aluminum octahedron together, and then you have water held in between the layers, and then this repeats itself over and over again. Because of the electrical charge on the surfaces, we get an affinity for water, and water appears in the montmorillonite particles, and then gets attracted to montmorillonite particles. And illite's very similar to the montmorillonite particle, except instead of having water intermittently, it ends up having a potassium ion. There are other clay minerals that are similar to this, and part of the reason we have some additional clay minerals is, if you go back to the previous slide, there is sometimes substitution for some of these ions, called isomorphic substitution. You can get small changes in the chemical makeup and have some slightly different clays, but these are kind of some of the basic clays that we've got out there: the kaolinite, montmorillonite, illite. The way these building blocks come together gives clay a very interesting behavior. And we'll look at this is really defined by what we see on this slide. Let's start around at the bottom of the kaolinite particle. So the kaolinite particle is typically about 50 to 2,000 nanometers thick and 300 to 4,000 nanometers in diameter. And it has a specific surface. So if I took all those particles in a kilogram of mass, it would have 0.015 square kilometers of surface area. Now let's go up here to the montmorillonite particle. It's 3 nanometers thick. Remember the slide I showed you with kaolinite, montmorillonite? The difference is that montmorillonite is just paper thin. And then the diameter is 100 to 1,000 nanometers. You have a huge length and width when compared to its thickness. And you end up with a specific surface of 0.8 of a square kilometer per kilogram. That's a substantial number. So that surface area gives lots of places for water to want to stick to montmorillonite. So montmorillonite has a huge affinity for water for that reason. Even if it's a montmorillonite clay, you might be worried about being a swelling clay because it wants to grab onto that water and hold on to it. So I think I had a little break here. So thinking about how many square kilometers of surface area is there in 5 pounds of montmorillonite or 5 pounds of kaolinite. And I probably should have put kilograms because my last slide was in kilograms. But it's so just thinking about that. So if I went back and looked at the previous page, you know, I have for the kaolinite 0.015. So I just multiplied. So if I went back to kilograms, multiply this by 5, would be 5 times 0.015 would be 0.075. If I went to the montmorillonite and multiplied that by 5, so 5 times 0.8 would be 4 square kilometers in 5 pounds, which I thought like a 5-pound bag of sugar is a good analogy to the 5 pounds of montmorillonite clay. And imagine 4 square kilometers of surface area. That's pretty substantial to us. So when you talk about clays and you think about clay behavior, we'll use the term cohesion later and cohesive strength. A lot of the reason we have this cohesive strength is because of the affinity clay has with water. And then when we get into classification, being able to measure in the laboratory what kind of affinity the clay has for water will help us define whether it's a montmorillonite kind of clay or a kaolinite kind of clay when we do the classifications. There's a reason why we're looking at the mineralogies, because it helps define the behavior down the road. So with that being said about soil particles, the thing we really want to build to is soil classification. At the end of the day, I want to be able to hand everyone, say if I handed a soil sample to everyone that's a participant here, we want to have a system to where everybody could take the same soil sample and conduct the same test, apply the same method, and get the same result. You don't want to have a judgment-only way of determining, so it's a clay, it's a sand, it's a silty clay, it's a silty sand. You want to have a definitive way to define the soil type. And what we're going to do is we're going to look at soil classification in terms of the index properties we need to determine, and then the classification systems that are popular. So the index properties that the classifications are routinely based on are going to be grain size distribution and the Atterberg limits, which is the plasticity, the affinity for water that the clay would have. And then look at the classification systems. The one that if you're doing non-highway work is the Unified Soil Classification System. And then for highway work, you're going to see the American Association of State Highway and Transportation Officials that we call, of course, the AASHTO system. You probably have seen both before, and they're very similar methods. So grain size distributions, you probably remember this from your soils class from before, where we determine the percent finer by a sieving or sedimentation test. We're going to pass soil through several sieves that are grading smaller as we go down to a pan at the bottom. And of course, we're going to have different the different soil grains are going to be sorted in size. And then we'll weigh these pans or these sieves and determine the relative proportion of that grain size. The other test that we would run would be a hydrometer test, where we take soil and put it in a suspension, and we allow it to for the soil to precipitate out of the suspension over time. You can't see it here very well, but there's a hydrometer in this cylinder here, and the specific gravity of this suspension changes over time. And we have a set of calculations set up that if we measure the time and the specific gravity, we can build the remainder of the grain size distribution based on that behavior. And the reason we use the sedimentation test, or sometimes called the hydrometer test, is that once you get the small particles like clay particles that are plate-sized, they don't do so well in a sieve anymore. And so it's a lot easier to do this test rather than try to force a bunch of plates that are, very, very, very wide as opposed to their thickness, like those montmorillonite particles. They don't do so well on a sieve, and we really need to use a hydrometer to do that kind of test. So just as an example, just to show you some numbers, here's a grain size distribution that I show my class every semester about how we would have the sieve opening size as the grain size, the mass of the sieve, the mass of the soil in the sieve, and we can determine the mass of the soil subtracting out the mass of the sieve. Then we calculate the percent retained. So this will be the percentage of the mass of the soil divided by the total mass gives us the percent retained. We want to know the cumulative percent retained then is, so we add these numbers in this column together, and then this becomes the result, and it should end up being 100% at the bottom that's retained. And the last step is to subtract that from 100, because all of our classification systems are in cumulative percent passing. So that says that 91.65% of the soil was finer than the 9.5 millimeter grain size. Now on this level, 64.22% was finer than the 2 millimeter grain size, and so on and so forth. We get down to the last line that I did not label. This is the pan. This is what passed through all the sieves and we still have left over. And the pan, whatever the last sieve of the pan, should be 0% passing. Everything should have been retained by then. Should have anything past that. To plot this data just looks like this. We have a grain size distribution on a logarithmic scale that runs reverse on the horizontal. So this is the particle size. And this is probably spaced out pretty high, going down to smaller numbers. Particle diameter in millimeters, and then the percent finer by weight coming down from the top. And this is how this information is typically presented. And you see the grain size distribution curve for the soil that I just showed you. Typical grain size. We will need to get some things off of this grain size distribution, and I'll call your attention to a few items here. Here's the number 4 sieve size, and I have it drawn in right here on my plot. Here's the number 10 sieve size, drawn in right here on my plot. I should use my pointer. Number 10 sieve size. Here's the number 40 sieve size, and the number 200 sieve size. The number 200 is the marker that says that delineates where we go from sand-sized particles to silt and clay-sized particles. And this soil, because it was my classroom example, didn't really have anything that was that small. But we'll be looking at this number 200 very routinely to see how much silt and clay we have. The 40, number 10, and number 4 help us define sand versus gravel. And we'll use those in the classification systems looking at those sizes. We'll also be looking at diameters that are 60% passing, 30% passing, and 10% passing. And you'll see those in the next slide about how we're going to use them. But think about going into this plot, going over and reading off what particle diameter is 60% finer, or 30%. So think about going across this line and then finding here what's 30% finer. And the same thing with the 10%, but this one doesn't extend down far enough. We'll need to pull numbers off of a plot like this. So let's go and look at the next page about how we would use this. Oh, just real quick, a couple of examples. I plotted grain size distributions, and we're just looking at these grain size distributions. If you had a very gently sloping grain size distribution, you would call that a well-graded soil. That means there's quite a variety of soil particles, and they're very well sorted. There's relatively even proportions of grain sizes in the soil. So relatively even proportions. It's a gentle slope. But a uniformly graded soil starts out sloping and then quickly falls around a grain size and then is done. That means that the majority of this soil has this grain size that's represented by the small zone right here. So that means it's very uniform. It has predominantly one grain size, and sometimes it's called poorly graded versus a well-graded material. And the last thing is a gap-graded soil, which you can see where you have a couple of grain sizes. So in this case, a gap-graded, you have a lot of grain sizes around this one, a lot of grains around this size, and then everything else is in relatively small proportions. So it's a gap-graded soil. You don't have, it's not well-graded, it's not uniformly, it's another kind of strange grain size. I said we need to use some index properties from that grain size distribution. So the first one is the D10 particle size with 10% finer. That D10, we're going to use it in our calculations, but it's also relative. You've seen it. You'll see it when you talk about permeability, as it defines the kind of the effective size, and it can whatever is 10% finer can define the permeability of the soil. And if you're talking about capillarity as well. We're going to need it, though, in our uniformity calculation. The D60 is the particle size with 60% finer, D30 particle size with 30% finer. In order to look at coarse grain, coarse fractions, the coarse part of the soil, we'll look at the coefficient of uniformity, the CU value, which is just D60 over D10. And then we'll look at the coefficient of curvature, which is D30 squared over D60 times D10. And we'll use those two numbers in the grain size distribution to help determine if it's a poorly graded or well-graded sand or gravel. Then the fine fraction properties we're going to borrow from Atterberg limits. And you may remember doing this stuff back in undergraduate soils. But just as a real quick reminder, if you take a clay or a silt and you add water to that material, say I start at the left where it says volume of water equals 0. The total soil volume is going to start at some number. As we begin to add water to that, we're going to fill up voids up to a point. And then eventually, as we add additional water, the volume of the soil will expand. The point where the soil just starts to expand is the shrinkage limit. we begin to add more water, more water, more water, the soil is going to go from the semi-solid state to the plastic state. The boundary between the semi-solid state and the plastic state is called the plastic limit. Then as we add additional water, the soil goes through its plastic phase, and eventually the soil is going to become very liquid-like. And that's the liquid limit. We're going to use the liquid limit and the plastic limit from the Atterberg limits as a way to define what the plasticity is of the fine materials, and it'll help us determine if it's clay or silt, and then what kind of clay or silt that we have. So we're going to use the liquid limit as one number, and then we're going to determine what's called the plasticity index, the PI, which is the liquid limit minus the plastic limit. And we're going to use the liquid limit and the plasticity index in our calculation. So you probably all remember this. We all suffered through it. The Atterberg limits test, the plastic limit test here on the right, where you're rolling out soil into little threads. When the thread was about 1/8 inch in diameter and it crumbled, that was the plastic limit. The liquid limit on the left, that was the Casa Grande cup, where we cut a little groove in some soil and you turn this crank, and when the groove closed at 25 crank or drops, that was about where the soil was at its liquid limit. So we determine the water content here, that was the liquid limit. Determine the water content is the plastic limit, and those are our Atterberg limits. I know you probably can't see this well. I don't know how big your computer screen is. I struggled to get this on a screen at one level, and I hope you're able to print out a copy and have it in front of you. If you can't see it that well, let me explain it. This is the Unified Soil Classification System chart as presented by the Army Corps of Engineers. And the way this chart works is you move, and so the first major delineation is, it asks, is more than 50% of the soil retained on the number 200 sieve? If more than 50% is retained on the number 200 sieve, you're in the sand and gravel part of this chart. If more than 50% passes the number 200, you're down here in the fines part of the chart. So once we move over into, once you make that basic delineation, I'm going to go ahead and look at the fines part of the chart first. So we're down here on the bottom, which is the fines part of the chart. Once you're in this range, the only thing you have to do is look at the Atterberg limits values, the plastic limit and the liquid limit of the soil. What you would do is you come into this little chart right here in the middle, and you would go over your liquid limit on the bottom axis and the plasticity index on the vertical axis, and you would find which soil type you have. So the soil types available are going to be MH, which is a lean silt. MH is a fat silt. ML is a lean silt. CL is a lean clay, and CH is a fat clay. And the only other things we have on here are the organics, and I wouldn't worry about those. So you just have 4 categories. The lean silts, which are low plasticity, the lean clays are low plasticity, and the fat clays and fat silts are a little bit higher plasticity. So that's the only thing you need to do to determine the soil classification. Go back up to the top and you have the coarse fraction. Then if you have more than 50% is retained on the number on the number 200, then you have a few decisions that you have to make. And that would be, I'm going to bring us over right here to this little block on the chart. If it's less than 5% for passing the number 200 sieve, then you have 4 choices. You either have a well-graded gravel or a poorly graded gravel or a well-graded sand or a poorly graded sand. It's just GW, GP, or SW or SP. That means that you have very, very little fine material. The second thing is if you have more than 12% fine materials, then you would have the classification as either a silty or clay gravel or a silty or clay sand. That'd be a significant number of fines with your gravel or sand. Now the fun part is if you have between 5 and 12%, you actually have to classify it by dual symbols. So it would be as if you're classifying it as a less than 5%, it would be you have to find the fraction of well-graded, poorly graded sand or gravel. And then you'd have to classify the fines as well. So it would be like, for example, if you had a sand with 50% fines, or sand with 40%, say 10% fines, then it could be a silty sand and a poorly graded sand at the same time. I'm not going to drag us that far down the rabbit hole. We're going to stick with some more basic classifications, but understand that you would have these dual classifications in that. Going back, if we had, say, less than 5% fines, and it's a poorly graded or well-graded gravel, or poorly graded or well-graded sand, and we're going to use those coefficient of uniformity and coefficient of curvature calculations that we had before to make that decision. So if it meets the criteria for a well-graded material, then we go with it. So for gravel, the coefficient of uniformity is greater than 4, and the coefficient of curvature is between 1 and 3. If it meets those, it's well-graded. If it does not meet, it's poorly graded. And the same thing for the sand. It would be greater than 6, it's well-graded. Greater than 6, and between 1 and 3, it's well-graded. If not, it's poorly graded. Then if we have more than 12% fines, then we have a sand with fines, and we do our first symbol is either sand or gravel based on the proportion of sand or gravel particles. And the second symbol is going to be silt or clay. So it could be a clay sand, a clay silty sand, or a clay gravel or silty gravel. And we would base that on where the Atterberg limits for that soil plot on the chart down here below. Do they plot below this line? If they plot below this line, then it's silty. If they plot above this line, it's going to be clay. Examples usually help us get through this, so we'll get to an example shortly. The other thing is the AASHTO classification system, and if you do a lot of highway work, you're going to see this. AASHTO, the way this classification system works is that you move from left to right, and the first category that your soil falls into is what the classification is. It may meet others from further to the right, but the very first one that it meets is the one that you'll use as classification. One thing I'll call your attention to is notice in the AASHTO that 35% fines is the dividing line rather than 50% had on the USCS. So it only takes 35% fines to make it a fine grain soil, where with the USCS it was 50%. And we just look at the relative grain distribution for the number 10 sieve, the number 40, and the number 200. So now you can see why I put those delineations on that original chart that I showed you. So we'll just go in and read off the chart which one it meets as far as grain sizes, and then depending on the soil type, and then we'll examine the Atterberg limits, and still have the liquid limit and plasticity index, just like the USCS table. The thing about the AASHTO is we go from excellent roadway soils to fair to poor roadway soils, and that's how this thing is classified. So A1s will be the best ones, and A7s are going to be the worst. Had a very similar plasticity chart where we can see the Atterberg limits again. This is almost like the USCS chart, where we're looking at the liquid limit and plasticity index, and that gives us where these A values are for our soils. So if you're going back, it helps us define what we see here at the bottom. The same thing about A2 soils, A4, 5s, and 6s, and they show up over here, A2, 6, A2, 4, A6. So we can also use the Atterberg limits on this chart for the AASHTO system. So, like I said, examples make a big difference here, and they always help me. So let's look at a couple of examples, and then I'll give us a chance to work them together. So I have several grain size distributions from a textbook, and at the bottom here's a chart that shows for each soil sample that we're examining. Some of them have Atterberg limits. So soil 1, soil 3, and soil 4 have Atterberg limits. Soil 2 and 5 say their fines are non-plastic. Means that when they did Atterberg limits, they didn't have enough fines to do it, or it came out as having a plasticity index of 0. So let's classify a couple of these. So the first one, look at soil number 3. So I've got soil number 3 over here. And the first thing that jumps out at me about soil number 3, this is the number 200 sieve size. In terms of the USCS classification, I have about 95% passes the number 200. So I'm immediately saying that this is a silver clay. So if I go in and say it's a silver clay, I need to look at my Atterberg limits. So I have a liquid limit of 124 and a plasticity index of 77. So let me back up here. So 124 and 77, just to show you on this chart right here, it goes to 100. If I had to extrapolate out a little bit down here at the bottom, 124 and 77 to me is going to be above this line, probably up in here. So the classification for this material is a CH using an extrapolation. I'll go to the AASHTO system with those Atterberg limits of 124 and 77. So 124 and 77. Back to the AASHTO for just a second. So 124 and 77. If I look at going across the bottom, looking at Atterberg limits, I need to look at the liquid limit of 124. I have a 41 min and 10 max for the A2. It doesn't work. 41 min and 10 min for the A27, but I have 35% max passes the number 200, so I don't fit in the A2 categories. I go into the A4, 5s, and 6s. So 40 max and 10 max, no, that doesn't work. 41 min, 10 max for A5 doesn't work. 40 max, 11 min doesn't work. This is an A7 soil. So that's why I got A7. 41 min, 11 min. That means we have a pretty highly plastic material. That fits kind of with the CH idea as well. So soil 3, CH by USCS, A7 by AASHTO. Soil number 5. Less than 5% passes the number 200 sieve. 25% passes the number 4 sieve, which is the delineation between sand and gravel. So that means that everything from here to there is gravel, which means about 75% of this soil is going to be a gravel. So that's why I went ahead and wrote down, this is a gravel. It's a gravel. I had less than 5% passes the number 200 sieves, so I'm kind of in a clean gravel here. So all I do is I'm going to check the coefficient of uniformity and check the coefficient of curvature. So D10, if I read off D10, so I come over here at the 10, and then I read off, come down here at the bottom and see what D10 is. And I said D10 was about 0.5 millimeters. I want to see what D30 is. So come over to 30. And then come down here, and D30 is about 11 millimeters. And then D60, come all the way down here to the axis, D60 was about 30 millimeters on that log scale. So the coefficient of uniformity was D60 over D10 was 60, 30 over 0.5. And the coefficient of curvature is D30 squared over D60 times D10. I ended up with a 4.03 for the coefficient of curvature. So if I go back to the USCS quickly, at a coefficient of uniformity of 60 and coefficient of curvature of 4.03. I'm up here at the top. So coefficient of uniformity has to be greater than 4. Coefficient of curvature has to be between 1 and 3. Well, I don't meet both criteria, so it will be a poorly graded gravel, a GP. Going to the AASHTO system, looking at a little bit more about the grain size, is I had 18% passes the number 10, and 10% passes the number 40. So 18 passes the number 10, and 10% passes the number 40. Well, 50 max works for both. 50 max for the number 10, and 30 max for the number 40. That, and then I had 5% passes the number 200. So it meets everything for the A1A classification. So that soil became an A1, is an A1A by AASHTO. And then I thought together we would look at soil number 4. So think about soil number 4. If I'm classifying soil number 4, the very first thing, think about a USCS type classification. I'm going to come over here to the number 200 sieve and look at this percentage passing. First thing that comes to mind is this thing is sitting at about 70% passes the number 200. So as someone who's going to classify the soil, I would immediately go over and say, okay, I need to look at the Atterberg limits now for soil number 4. Soil number 4 has Atterberg limits of liquid limit is 49, and the plasticity index is 25. So 49 and 25 are the numbers I'm looking for. So I'm going to go back to my USCS at 49, which is right here by 50 and 25. It's just above this line, and it will be a CL, a lean clay. So it's at 49 and 25. Soil number 4 will be a CL. Turned out yellow. CL. So just an example of how we could use this. I just wanted to show you. Kind of gave us a little bit of a breather. So soil classification. Again, the whole idea is that I can ask anybody to take these soils and do the exact same classification test. Look at these grain size distributions, look at the Atterberg limits. We could take a sample of any soil and we could do those individually and follow the standard test and arrive at the exact same classification. And that's the main goal of classification. Now, the other part of it is thinking from the contractor side of it is you want to be able to identify these soils, especially for design. We won't be able to say, oh, we in sand or clay. You don't know that, because the behavior is going to be fundamentally different. If you have a lot of silt in your sand or a lot of sandy clay or something like that, these are things we need to know. So we want to trust whoever's doing the soil test for us that they follow the same procedures and they're going to give us a consistent soil type that we would expect. So that's classification. The next thing is moisture, volume, mass relationships for soil. Now, you probably heard this as phase diagrams and phase relations. This is bread and butter geotechnical engineering 101 stuff. And we're here to review how we can use this to define quantities. And we'll look at the phase relationships, do a couple of quick examples, but I think the most important thing for most of us is looking at the bar and fill aspects. This is huge for construction, and that's where I think that the biggest application comes in. What we're going to do is we're going to take this, remember our picture from before, we have soil as a group of particles with air and water, and magically separate into 3 different phases, and then look at the relationship between these phases, and find some derived relationships, and then go back and forth and calculate what their relative proportions are. Again, that's a big deal when we talk about bar and fill problems. We're going to use this thing called the phase diagram. You probably remember seeing it in the past where we have air, water, and solids. On the right side, we've got weight or mass, where the water has weight or mass, the solids in the soil have weight or mass, and we have a total weight or mass of the soil. On the left side is the volume. So the air has volume, the water has volume, and the solids have volume, and they have a total volume together. And I'll try to stick to these symbols as we go. The key to it is to remember to go from volume to mass. We just have to multiply times the unit weight, which will be gamma, or the density will be rho. To come back from the mass side to the volume side, we're just going to divide by the unit weight or the density. And you'll see density a lot when we're working in SI units, but unit weights are probably more popular in American units. So I'm going to do some things in a little bit of both just so we can remember that. So the basic definitions are densities. So total density, density of water, density of the solids, dry density of the soil. And call your attention to the density of solids is oftentimes we see expressed as a specific gravity times the density of water. So the specific gravity being the proportion between the density of water and the density of a particle. So that's our basic definition. The same definitions work for unit weight. So total unit weight of water, unit weight of the soil solids, and the dry unit weight. Dry unit weight is commonly used, and it's just the weight of the solid particles divided by the total volume. Very, very commonly used in compaction applications and compaction inspection. And just a reminder that the weight is just the mass times the gravity, and the unit weight is just density times gravity. And again, density and mass in terms of English units is cumbersome, so we typically work in weight and unit weight. In SI or metric, we can go back and forth between the two because we're comfortable with kilograms and we're comfortable with kilograms, but we're not comfortable with slugs, we like pounds. Some Some derived quantities you're going to see are water content, a measure of how much water is in the soil, weight of water divided by weight of solids, times 100%, can be greater than 100%. The void ratio, the volume of voids divided by volume of solids, expressed as a fraction, and that can be greater than 100%. You can have high void ratio soils. Porosity, volume of voids divided by total volume times 100% can only be between 0 and 100%. And the saturation, volume of water divided by volume of voids, a measure of how much water is in the voids, is also a number that can't be greater than 100%. So we can use these derived quantities, and some of these are the way information could be presented to you about a soil that you're using for a borrow. They get the void ratio, you definitely get the water content, and you may hear something about the saturation. So some typical values that we might want to use here. Oftentimes the specific gravity of the solids is assumed, and it doesn't vary that much. So the solid particles, depending if they're quartz or kaolinite, basically sand particles or clay particles from somewhere between 2.6 and 2.7 is the specific gravity. You would multiply that times the unit weight of water to get the density or unit weight of the solids. And then some rules of thumb. Now, unit weight of water doesn't change. It's 62.4 pounds per cubic foot, or 9.81 kilonewtons per meter cubed. And soil, my best guesses are usually between about 100 and 125 pounds per cubic foot, which comes out to be about 15.7 to 19.7 kilonewtons per meter cubed. Again, these numbers are usually reasonably safe to estimate in geotechnical terms, so I like to use just some round numbers in here as far as unit weight. When we solve problems sometimes, and again, these may be more textbook problems, but sometimes we'll just be given the void ratio of the water content and have to come up with a solution. In those cases, we could always make an assumption about the volume to help us with our proportionality. And usually we'll assume that the volume of the solid particles is going to be about 1 unit, 1 cubic foot, 1 cubic meter. If we're given total densities or dry densities, then oftentimes it's more convenient to assume the total volume is 1, because then we can use that density to our advantage and then continue to calculate. These only really come into play, though, when you're not looking at specific volumes. When you have a soil that you just have some basic properties for and you want to find out another basic property. When you get into having finite volumes, that makes it a little different. And I'm going to work two problems. One has finite volumes and one doesn't, and show you where this comes into play. So I'm going to look at an example kind of quick here. I've got a soil have a total mass of 18.1 kilograms, and that 18.1 kilograms is in a volume of 0.009 cubic meters. And then the mass of solids was found to be 16.13 kilograms, and the specific gravity of the solids was 2.7. And the find here is to find the total density, find the dry unit weight. And I do mean to go between density and unit weight. Find the void ratio, find the water content, and find the saturation. If the specific gravity of the solids is 2.7, then the unit weight of the solids is 2.7 times 9.81 is 26.48 kilonewtons per meter cubed. I went ahead and set that up based on the given information. So I've already filled in the phase diagram up here, but I'm going to show you how I got to all these numbers. Some of the stuff was given. We had a total mass of 18.18 kilograms. That was given. We're also given the mass of the solid, as if we dried that out in the oven, and we got 16.13 kilograms. So the difference between these two becomes the mass of the water, and I calculated the mass of the water here first. Well, I know from the mass of the water, I know what the volume of water is just by dividing by the unit weight of water, which is the unit weight of water, or the density of water is 1,000 kilograms per meter cubed. I divide 2.05 kilograms divided by 1,000 gives me 0.0021 cubic meters, which is this number here. The volume of the solids then is moving from this side of the diagram where I have mass of solids of 16.13. Divide that by the specific gravity of solids times the density of water, 2.7 times 1,000. I divide 16.13 by that, I get 0.0059. And then I have this volume, I have I have the volume of water, I have the volume of solids, and to find the volume of air, I just subtract them from the other volume that I already knew. Remember, 0.009 was given. 0.009 minus 0.0021 minus 0.0059, and I get 0.001 cubic meters of air. Now I have my entire diagram filled out, and I can calculate any quantity that I want to as far as a derived quantity. So the water content is the mass of water over mass of solids times 100%. So 2.05 over 16.13 times 100% is 12.7. The void ratio is the volume of voids divided by volume of solids. So I have the volume of voids is the volume of air plus the volume of water divided by volume of solids. I got 0.53. The saturation volume of water divided by the volume of voids. So 0.0021 divided by the sum of the volume of air plus the volume of water times 100%. I got a saturation of 67.7%. The dry unit weight would be this: 16.13 kilograms. To get from kilograms to kilonewtons, I multiply times 9.81. I multiply times gravity. Divided by 0.009 was the total volume. I get 17.6 kilonewtons per meter cubed. And then to go back to calculate the total density then is the total mass, 16.13 plus 2.05 divided by the total volume we started with, was 2020 kilograms per meter cubed. So my approach to these problems I typically teach my students is to draw this diagram whenever I need it, and I can fill in and determine my quantities and then go back and calculate everything. I like to really work hard to understand the diagram and to make it work for us, because it's a very easy. You just move back and forth, knowing the relationship between volume, density, and mass. So the second problem illustrated is one of these where I don't have a finite volume. I can make an assumption. So the second problem, I have a unit weight of 110 pounds per cubic foot, a water content of 10%. I want to find the dry unit weight, the void ratio, the porosity, the saturation, and the saturated unit weight. I'm going to make an assumption here that the specific gravity of solids is 2.7, so the unit weight of solids is 2.7 times 62.4 is 168.5. Now I'm going to assume that the volume of solids is 1.0, because again, I didn't have anything given. I didn't have a finite volume given. So I drop my assumption here, that 1.0 cubic feet the volume of solids right here in my phase diagram, and begin to use that to make calculations. So if the volume of solids is 1, then the weight of solids is the volume of solids times the unit weight of solids. That's 1 times 168.5, so I have 168.5 pounds of solids. The water content was given as 10%, so 10% times the weight of the solids is the weight of the water. I get 16.85 pounds. I add those two together and I have a total weight of 185.4 pounds. So I've determined my weight side of the diagram. If I go back across, the volume of water, the weight of water over the unit weight is 0.27 cubic feet. I knew the volume of solids already. The total volume is the total weight divided by the total unit weight. The total weight was 185.4. I calculated that. The unit weight was given was 110 pounds per cubic foot. I get 1.69 cubic feet for the total volume. Then to find the air, I just take the total, just like we did last time. So take the total volume minus the volume of solids minus the volume of water. I get a volume of air of 0.42 cubic feet. Again, my diagram is now filled out. Now I'll get to go in and make the calculations that I need. So I start with the void ratio. Volume of voids over volume of solids. Volume of solids was assumed at 1. Volume of voids is the water plus the air. I got 0.69. Porosity is volume of voids divided by the total volume is 0.41. Saturation, volume of water divided by volume of voids, so 0.27 was the volume of water. Volume of voids, 0.42 plus 0.27 times 100% was 39%. The dry unit weight then was the weight of the solids divided by the total volume. 1.168.5 divided by 1.69 is 99.7 pounds per cubic foot. And then the saturated unit weight is a little bit of a trick here, because I need to have all the weight of the solids plus take all the void space and fill up every bit of it with water. So I got to have all this water first, plus I'm going to take this 0.42 cubic feet and fill it with water as well. So I just said 0.69 cubic feet was the volume of voids times 62.4 pounds per cubic foot, and that fills up all the voids with water. Divide that by 1.69 cubic feet, I get 125.2 pounds per cubic foot. Again, these are kind of academic examples. It's just to get us comfortable with using this diagram, filling it in and going back and forth and using the relationship between mass, volume, and weight. What I really think is important, though, is the borrow and fill problem. Once I finish this, then it's going to be time to take a break. I think we all need a little bit of a breather here. The borrow and fill problem looks like this. We've got a borrowed pit and an embankment. I've got my borrowed pit properties, 108 pounds per cubic foot total, water content of 12%, specific gravity of solids is 2.7. My embankment has 115 pounds per cubic foot dry unit weight in place. It's going to have water content of 15% by spec, and the volume of that embankment is 270,000 cubic feet. So I'm going to have to buy bars, so I need to know how much I need to buy. So what's the volume of the bar that I need to buy, and then how much water do I need to add in to make that embankment at 15% water content, which, how many water trucks you need to bring in. So the way we start these problems is we always start on the fill side. We know what the total volume of the fill is, and our specification had a dry unit weight of the fill, so that makes it easy for us to start our calculations. So the weight of the solids in the fill is going to be the dry unit weight times the total volume, 115 pounds per cubic foot times the 270,000 gives me 3.105 times 10 to the 7th pounds. It's a lot. It's a big embankment, so we're in scientific notation. The weight of the water then, well, I had a 15% specification on the water content, so 15% of that solids is 4.658 times 10 to the 6th pounds of water. And I'm calculating it now because we're going to need it when we calculate the amount of water we need to add. So what I need to do is remember this 3.105 times 10 to the 7th. We need to take that weight of solids and take it back over to the bar. Because in the process, we can add more water, we can dry it out, we can try to get more air in and take air out, but we can't produce any more solids. The solids are what we have to get from the bar, technically. So I put that weight of the solids over on the bar side. If I have that much solids on the bar side, the bar had 12% water, so I need to multiply times 12%, gives me 3.726 times 10 to the 6th pounds is how much water is in that bar for that much solids. And the total weight is just add these two together, 3.478 times 10 to the 7th. The total volume then is the total weight over the total unit weight. The total unit weight of this bar was given. So 3.478 times 10 to the 7th divided by 108 pounds per cubic foot says I need to get 322,000 cubic feet of the bar to make 270,000 cubic feet of the fill. So that's the answer to the first question, 322,000. The second thing is how much water do I need to add? So basically the water in the fill minus the water in the bar. So we calculate on the fill side 4.658 times 10 to the 6th pounds minus 3.7626 times 10 to the 6th pounds. And the net difference is 931,500 pounds of water, which comes out to be about 150,000 cubic feet of water. So, 15,000 cubic feet or about 110,000 gallons of water. So it's a substantial amount of water we've got to add into that fill to make that specification. I like that problem because I think to me, it gives the right context for all this work with these phase diagrams, is the real true construction side of the problem. And with that, I think it'd be a good time to go ahead and take a break a little early. I think we're just right a little over an hour in. Only take about how long do you think we should take, Sarah? 5 minutes?
At least, yeah.
Maybe take 10 if you
for it.
Okay, why don't we do 10 minutes, and then we'll come back in 10 minutes and we'll resume. One logical outgrowth of the uh, uh, cut and fill problems is compaction. And again, as contractors, you're probably very familiar with this. I just want to review a little bit about compaction and then do a little quick calculation about compaction inspection. This was actually going to be my timeout slide, so we're back in. Compaction, the purpose of compaction is to actually reduce the volume of air and get the soil to probably its densest state possible. We're going to look a little bit about equipment, talk about laboratory specifications. In the lab specs, we're going to talk about maximum dry unit weight, optimum water content. That's what we want to find in the lab, and we'll talk about that one. And then in terms of field measurement, there are different field ways of measuring. You want to be able to inspect the density and compare it back to our specification, and we'll look at how we would do that, the sand cone balloon, drive sampler, and gauge. So compaction kind of has four purposes. One is to ensure the adequate strength. When you're going to place fill in a location, you want to be able to say that it's going to, you can't just dump it there and walk away from it. You've got to ensure that it's going to have the strength that you're going to build on. I mean, we're going to reduce the compressibility. We don't want it to settle. We get all that settlement out of it. We want to stabilize against volume change. And we want to ensure proper permeability. It has more to do with that building liners and anything you need to make sure is supposed to be impermeable or supposed to be permeable one way or the other. So some principles. So sands are the easiest to compact. We get higher strength when we compact, lower compressibility, and usually increase the permeability of sand when compacted. Silts, on the other hand, are difficult to compact wet. They have we're going to reduce the volume change when we compact them, and probably reduce the permeability. Clays are very difficult to compact wet. The compaction will increase the strength and will decrease the permeability, that's what we want. So think about compacting a landfill liner. We want to decrease that permeability. The clays can be unstable for volume changes too, when not compacted. So just a review of compaction equipment. This is something you guys are probably all experts with. But for clays, we're typically using something like either a sheep's foot roller that does tamping compaction, has pretty high contact pressure, and we usually compact in about 3 to 5 passes and about 6 to 12 inches of soil at a time. These things literally just walk out as we compact, and really want that kneading or tamping type compaction to get the clay kind of worked into its most dense state. Similar to with clay, similar to the sheep's foot roller, you have a pneumatic tire roller, and that's a kneading type compaction. Usually a heavy roller. We can compact about 6 to 12 inches of soil at a time. I'm usually going to go back and forth about 3 to 5 times. And again, if you look at these axles here, the whole idea is that you're kneading the soil, because those axles all can move independently. So you kind of have an up and down motion side to side, and can potentially, the whole idea is to knead the soil and compact it into a denser state. When you think about sands, usually we're going to compact with some kind of a vibratory compactor, a smooth drum or a pneumatic tire roller that vibrates, has a high frequency and low amplitude vibration, using about 1,500 to 2,000 cycles per minute, moving kind of slow, 2 to 4 miles per hour, 3 to 5 passes. Again, you're looking at about a foot, usually about a 12-inch lift is what you're going to compact at any given time. And again, the compaction usually, it doesn't matter how many. Usually only have a few passes. 3 to 5 passes is plenty to get compaction in any soil. Except you can't. There's a limit as to how much compactive effort you're going to be able to impart. It's not like you could do 50 passes and get any better compaction than 5. We need to set a specification for density, and the typical specification we're calibrated to is the Proctor density. I didn't write Proctor on here, but I'm going to write it here. So this is Proctor. The Proctor density. And what we're going to do is go to the lab, and we're going to take some soil. Here's the molds for the Proctor molds right here. We're going to fill up these molds with soil. We're going to create specimens by compacting inside of this mold at increasing water content. So think about this plot moving from left to right, increasing water content. We're going to get, and then as we increase water content, if we were to mold the soil and then determine what the unit weight is, and then determine the dry unit weight, then the dry unit weight will approach a peak. And then after you begin to add additional water, once you hit that peak, then you'll get to the point you are getting wetter and wetter and wetter and wetter, and you'll lose that dry density. So at some point, water acts as almost a lubricant to help the soil pack tighter and tighter together. Eventually, we get to that maximum point where we are at the best, the maximum dry density or maximum dry unit weight. And beyond that, water becomes more void space and begins to kind of loosen the soil up, and we get a lower dry density. So what we're trying to find is this point right here where we have the gamma D max, the maximum dry unit weight, and then corresponding to that is the water content that gets us there. And we call that the optimum water content. So the goal of doing the Proctor density lab test is to find that point, because we want to have that point to help set our specification for the field. In the field, we usually have a spec, and it's probably something like 95% of the gamma D max. So we're going to say, I'm going to multiply that gamma D max times 95%, and we've got to at least get that number. And the water content, in terms of rough numbers, again, is usually within about 2% plus or minus of the optimum water content. Again, it gives the inspector in the field something to judge by when he does a field density inspection to say, okay, I know what my gamma D max in the field is. Doesn't meet this criteria. Doesn't meet this water content. If it passes, yes, we'll accept the fill. If it doesn't pass, then we're going to have to rip it up and redo it. So the field measurements are, again, a way of providing an inspection against that Proctor density. So the different ways that we devised to do this in the field, the first ones are really based on how can we measure the volume of the hole that we create to get the density sample from. And the way we measure that volume is the sand cone, a balloon apparatus, or a drive sampler. And the whole idea is we're going to excavate a hole, measure the volume with one of those devices, and weigh the excavated soil and determine its water content. And we can arrive at the unit weight, the unit weight of the soil. The sand cone looks like this. It's kind of like an hourglass. The sand inside of the stuff is density sand. It's something you can buy from a geotechnical supply company. And what happens is we excavate a hole down here, and then we put this plate on it with a cone up above it. And when the sand is going to flow from this bottle through this valve into the cone and into the hole. Now, however much sand is lost out of this bottle, we can weigh that. We know how much sand goes into the cone, and we can get rid of that too, just by, the volume of the cone. Whatever's left down here that went in the hole is what we want to know. So by subtraction, we can find the volume of the hole. That's the sand cone test. Another way we can measure the volume of the hole is the balloon apparatus. And here on the right is a little cartoon of the balloon apparatus. Again, we've got another hole that we've excavated in the ground. We've collected all that soil. We're going to weigh it and get its water content. We've got to find out what the volume of the hole is. So this balloon apparatus has a rubber balloon. You can see it over here on the left. It's attached to the bottom of this apparatus. And this is the rubber balloon now being inflated down against the soil in the cartoon on the right. So that rubber balloon attached to the bottom of the apparatus, there's water inside of this watch glass. So as we put the balloon on the bottom and we put the water inside, we can pump air into the top. That's what this little blood pressure bulb is right here. We're going to pump air in here and force the water to push on the balloon and then make it touch the sides of the excavation of the hole. And as this water falls in the watch glass, we get an indication what the volume is. So we can measure pretty directly what the volume change is just by displacement there, some balloon apparatus. Probably a more popular device right now is a drive sampler. This is a DCP hammer. You've probably seen that before. And instead of having the cone at the bottom of the DCP, there's literally a short piece of a sampling tube that's placed at the bottom. You just go down to inner grade and hammer this sampler into place, and you get a sample of a known volume that you can also use to find its density. I've seen this used a lot more often now because it gives you a physical specimen to take back and measure instead of just a regular hole like we have for the other two. The other method for determining field density is a completely different beast. It's a nuclear gauge. And what it's going to do is you're going to take this. There's a source of radiation that is in this device. It can either be placed at the surface, or a hole can be hammered or drilled in the soil, and the source can be placed down hole. What you're going to do is you're going to infer the density and water content of the soil based on the transmission and or backscatter of radiation. So if you put the source down hole, you'll have a transmission of radiation back to the receiver. And if you just leave the source on the surface, there'll be a kind of a bouncing of radiation back into the unit. So either by direct transmission or backscatter, you're going to measure what the water content and the unit weight are in the soil. These are very popular because they're very quick. You don't have to dig a hole. But the downside is, of course, you've got a radiation source out in the field, which is getting more unpopular by the day, unfortunately. So, but nuclear gauges are very expedient and a very popular way to do it. You're going to get density and water content just like you will get from the other methods. So let's look at an example here of a Proctor specification, and then also look at the field spec. So the data from the Proctor compaction test is as follows. So I have 6 Proctor tests that I ran. So six different water contents. I measured what the weight of the soil was inside a Proctor mold. The Proctor mold has a volume of 1/30th of a cubic foot, which is not accidental. Because if I want to take mass over volume, so I take mass over volume, so mass of 3.95 pounds divided by 1/30 cubic feet, which is just like multiplying by 30. So 3.95 times 30 is 118, and that's how I've calculated these gammas in this middle column. So 3.95 times 30 is 118, 4.88 times 30 is 122, and that's where all these numbers came from. Then I divide this column, the total unit weight, divided by the unit weight of water, plus 1. So 118.6 divided by 1 plus the water content, this equation right here, gives me the dry unit weight, which is what Proctor's density is plotted as. So I'm going to plot water content versus dry unit weight, and that's on the next page. So I plot the results of water content on the horizontal and dry unit weight on the vertical, and this is my Proctor curve for that soil that I just showed you. So you see again, unit weight's increasing as it increasing water content, and then once we hit the dry unit weight, gamma D max, then it starts to fall off. So from this plot, I went ahead and identified that my gamma D max was that top point there. If I go back to the previous slide, that was the ones highlighted in yellow, 106 and 18. So 106 and 18 are my gamma D max, and my optimum gamma D max is 106 pounds per cubic foot, and my optimum water content is 18%. Then, so if I go back and set a density spec, much like I mentioned before, then spec is 95% compaction at plus or minus 2 of the optimum water content. So 95% of 106 is 100.7, and then my water content needs to be within plus or minus 18% of 2%. So 16 to 20% is what the water content would be. So that's my spec, 100.7 pounds per cubic foot at 16 to 20% water content. So now I've run a field test. The field test happened to have the same volume. I said 1/30th of a cubic foot. The total weight of the soil that I pulled out of the ground was 4 pounds. I dried it, so the weight of the solids is 3.4 pounds. And the weight of the water then is the difference between the two is 0.6 pounds. The question I have to you to go ahead and ask is, does it pass the spec or not? How will I find that out? So all I need to do is to calculate what the dry unit weight is based on the numbers I've given. I've given you the volume, and I've given you the weight of the solids, so it's very quick to find what the dry unit weight is. 3.4 pounds times 30 is going to give me the dry unit weight. So 3.4 times 30 is 102 pounds per cubic foot. And the water content, excuse me, is I have the weight of the solids, I have the weight of the water. So 0.6 divided by 3.4 times 100% is 17.6%. So I'm asking, does it pass spec? Well, the water content was 17.6%, which is between 16 and 20%, so it checks. And my dry unit weight, again, was 3.4 divided by 1/30 is 102 pounds per cubic foot. So I did check out on my specs. So this test have a happy contractor because the inspector said it passed, I don't have to rip it out, and I can keep going. So again, kind of closing the loop a little bit on the phase diagrams and some of the moisture, volume, and mass relationships is between compaction and bars and fills. That's the biggest application. I think those have some good applications. So let's go ahead and move on to the next topic. I know we're kind of going fast, but next topic I want to cover is about stresses. Specifically when you get into design, a lot of with foundations especially, and earth retaining structures, is we've got to be able to define the stress state in the soil, and usually the starting point for our analysis. So let's quickly talk about stresses in the soil mass. So one of the most important aspects in geotechnical engineering is talking about effective stresses. And if I could explain effective stresses in the most straightforward fashion, it'd be kind of like this. I think about particle-to-particle contact is what the effective stress is. If we have voids in air or water, they do not carry any shear strength in soil at all. The shearing strength and the strength in soil is going to be based on grain-to-grain contact. So think about grain-to-grain contact, so I'm showing on the left. Is a soil grain actually touching another soil grain. I could have water pressure, I could have other things all around this, but right now I'm thinking about grain-to-grain contact. Now look at this picture on the right and then consider a couple of cross sections through a general soil. So if I just cut a cross section through soil on the top, this line is a cross section, it would actually go through the soil grains. And that isn't necessarily showing the contact to contact, that's just showing the true cross section. But this second line that goes through here is actually going through grain contacts. Kind of another dashed line here. So the wavy surface through the contact. And that's what these points would be. This is the actual amount of grain-to-grain contact I would have had in this cross-section. So let's start talking about effective stresses. That's the stresses that the soil skeleton transmits as it touches other soil particles. And, we'll talk about soil stress being carried by a couple of parts of the soil. We're going to talk about pore pressures and water pressures, and we'll talk about the soil skeleton and the effective stresses. And it's important the fact that loads may be carried by both of those pieces, but the strength is going to be based on the effective stress of the soil. So we calculate effective stress. This is how we lay it out. We start out with the total stress. Then we subtract off the pore water pressure. We calculate the pressure of the water. And the effective stress, which I'm going to delineate by sigma prime, is just the total stress minus the pore pressure, the effective stress. So again, effective stress is the pressure carried by the soil skeleton, and pore water pressure is carried by the pore water, so the water in the void. So almost think about this as saturated soils a little bit. There's water in the voids, and there's going to be kind of a buoyant effect. The water's can carry some stress, but it's not going to be able to give us any strength. So let's do an example of calculating effective stress. So at point P down here, which is midway in this 8-foot thick clay layer, I want to calculate what the effective stress is. Note the water table is right here at the bottom of this first sample. So to calculate the effective stress, the first thing I do is calculate the total stress, which in this case is just the sum of the unit weight times the thickness of the different layers. So the total stress would be 6 feet for the first layer times 100 pounds per cubic foot, plus 4 feet in the second layer times 118 pounds per cubic foot, plus 6 feet for the third layer times 126 pounds per cubic foot. And I'm going to go 4 feet to the midpoint of this clay layer times 120 pounds per cubic foot. So 600 plus 472 plus 756 plus 480 gives me 2,308 pounds per square foot of total stress at point P. The pore water pressure is just the height or the distance between this point and the water table level. So I have 4 feet to here, 6 feet to there, and another 4 feet to there is a total of 14 feet. So the pore water pressure is 14 feet times 62.4 pounds per cubic foot is 874 psf. So my effective stress is the total stress minus the pore pressure. So 2308 minus 874 is 1434 psf. Calculations like this are extremely routine, and when you get into the next phases of these sessions, you'll be calculating effective stress just like this often. So understanding this is a very key point here for any kind of geotechnical design. Another case of effective stress. This is kind of a neat little example that I've put together. I want to show you what happens if the water table rises, what happens with the effective stress. So just looking at these plots here. The water table is going to start out here down at the bottom of the problem. The ground surface is at 10 feet, and then we can actually go above the ground surface to elevation 0, so or depth 0. So at first, the water table is down at the bottom. So to calculate the vertical stress, the unit weight's 112 pounds per cubic foot. So 0, 11, 24, 22, 48. So this is 10 feet down and 20 feet down. There's no pool water pressure. So the effective stress is going to be, sigma V minus U. So there's no pool water pressure, so this effective stress is the same as the total stress in this first example. Let's move the water table up 10 feet. So if the water table rises to the 20-foot level, then my total stress is still the same. So 0, 11, 24, 22, 48. My pore pressure at 10 and 20 feet is still 0, but I now have pore pressure at 30 feet, 624 psi. And you see the impact on my effective stress is now my effective stress has gone down as the water table rose up. Less effective stress. Let's rise it up 10 more feet. Let's put it at the ground surface. The water table is up at 10 feet. Now my total stresses are still the same because I had a similar assumption for the unit weight. But my pore pressures are now 0, 624, and 1248, and now I've had a drop again in my effective stress, 0, 500, and 1000. The last thing I want to do is I want to put the water table above the ground surface. What impact does that have? This is what the impact has. I actually have to add into my total stress the water weight. The water now becomes a layer in this case. My pore pressures then are calculated just from elevation 0 down, 0, 624, 1248, 1872. But the interesting thing is that if I look back at the effective stress in case C and the effective stress in case D, the effective stress is stabilized and stays the same. So once the water table reaches the ground surface, then the effective stress no longer changes because above the ground surface you have pool water pressure and total stress are the same thing. So while the effective stress, continues to go up, stabilizes with the ground surface. Just a quick example of effective stress. The next thing we look at stresses beyond stress distributions, where the effective stress is kind of like the self-weight or the body stress of the soil. Now we need to look and see what we would do if we add a surface load and how that would change the stresses at depth. So some of the examples that I'll show you, there's more tables and methods that I'll present, but I'll show you some good examples are the 2-to-1 method where we spread the load, a point load equation, and a couple of influence charts are out there to calculate stress change. So this one thing that you might see is a pyramid approximation. Say you're out in the field and you've been asked to say, well, how much will this foundation increase the stress down at this level? You don't have anything but a cell phone with a calculator app and your mind to work with. This is the easiest thing you can do to start is just say that at a 2-to-1, we're going to say that at a 2-to-1 slope, that we're going to project this footing foundation area down at a 2-to-1 slope down to the next layer of where you're concerned about. And you'll take the same surface load and then spread it over a larger area, which is going to be a little bit of a decreased vertical stress. And this is just a very simple way of calculating what that change in stress would be. So if we go on to the next page, kind of shows you that if the change in vertical stress down at that level is just QBL. So Q is being the surface load times the original fluid dimensions BL divided by D plus Z, which is the original width plus the depth Z, times L plus Z, original length plus the depth Z. And that it becomes plus 1Z because you have half on each side because of the 2-to-1 relationship and just kind of multiplying it out. So it either becomes QBL or you just take that original, if it was a concentrated surface load, Q over B plus C times L plus C. Again, going back, we're just projecting this footing load down here at a larger area with depth that is just enlarged by by the depth. Very simple way of doing it. Again, if you're just out in the field and need to come up with a back of the envelope quick calculation, that's one way of coming up with it. Other ways of calculating what that stress change are typically attributed to a guy named Bouzinesq. You probably remember that from Soils 1. We had change in stress expressed as a fraction of the vertical surface load. So we're going to say that the change in vertical stress delta sigma V is some influence factor times the original surface load Q, or the contact stress. So the vertical, if I had a concentrated point load, like a column load or something, and I wanted to calculate what the change in vertical stress would be at some depth and some distance away from that load, then I could use this thing for a point load equation. Q times 3z cubed over 2 pi times r squared plus z squared to the 5 power. Again, this is Bouzinesq's solution by elastic theory that we use for the change in stress underneath the point load. Another way of doing it then, instead of just using an equation, is a chart. So, for example, here's a Bouzinesq chart for a circular loaded area at some depth z and some radial distance r away from the center. We can find what the change in vertical stress would be. So this chart is in terms of a couple of things. Z over A is the depth part of the equation, so the depth goes down the left side. Then values of R over A are all in these circles here. So you calculate R over A, where 2A is the diameter. So R over A is the radial distance away from the center divided by the radius. And then Z over A is the depth factor. And you can see how the load would change. And you find wherever this line intersects with your curve, and read off your influence value I at the top. And probably the most powerful chart, and again, I'm hoping that you got this in your packet, because it's kind of hard to read right here visually, but this is an extremely powerful chart. Is I call it the Fathom chart. It's the derivation for the increase in stress underneath the corner of a rectangular loaded area. So the power here is that if we have anything like an irregular shape or anything we need to build, if we can put them together in terms of rectangles that overlap at corners, then we can use this chart underneath the corner of any loaded rectangle, that we can build whatever shape that we would need based on that. And I'll do some examples to kind of really demonstrate how this works. It works out pretty well for us. So this first example, I just want to show you how I would use that circle chart. So I've got a tank, a storage tank, 24 meters in diameter. It's full of water down to 16 meters. I want to find the vertical effect, the stress change for points A through G. Some of them are on the center line, some are under the edge, and I've even got one that's a little bit away from the edge. First thing to do is find, I said it had water down to 16 meters, so what's the contact stress of this tank? So 16 meters times 9.81 kilonewtons per meter cubed is 157 kilopascals of contact stress at the base of the tank. So I want to see how that 157 kilopascals transmits down to all these points beneath the tank. So I just went ahead and set up a table here. So I think about, let me go back, it's points A, B, C, D, A, B, C, D, E, F, G. So A, C, and E are underneath the center line, B, D, and F are underneath the edge, and G is out by itself. So here's the A, the radius stays constant for all of them. So the A column stays constant. They have different Z's. So A and B at the same depth, C and D at the same depth, E through G are at the same depth. And then Z over A, then we have the radial distance away from the center line. So A, C, and E are at the center line. B, D, and F are at the edge, and then G goes out by itself away from the foundation. Then our value of R over A. And using R over A and Z over A, I went into the chart and found these different values of I. So just below the surface at the center, of course, it was going to be 157 kilopascals of contact stress. At point A, it was 0.9. At point B, it was 0.42. Point C, E, F, and G, and so on. So just the difference. Point A was underneath the center line. At the shallowest point was 141 kilopascals of stress transmitted, and then point G, which was away from the foundation, was only 11 kilopascals. And again, this is just a way of showing the diminishing effects of depth and radial distance away from the load that we would have, because you wouldn't necessarily say that a load is always going to be fully transmitted with depth. And that's what Booz-Ness solutions gives us. The other thing I want to do is do a few examples with the rectangular chart. These are just, I can kind of go through these relatively quick. This is just using that rectangular chart, which is, if I go back a couple of slides, this one, this general chart for rectangular area, using this chart for different permutations of a rectangular area. So you'll see for here, I've got this little example at, I've got a 6 foot by 3 foot rectangular area loaded at 1,000 PSF. So to find my influence value, I'm going to take, I'll calculate two things called M and N. So M is B over Z, which is the short width over Z, Z being 6 feet, the depth I'm interested to calculate the stress change at. So I have 3 over 6 is 0.5. N is the L over Z, so I have 6 feet divided by 6 feet is 1. I would take M and N and go into the chart. So 0.5 and 1, I would go into this chart. M or N is on this axis, and then these on the horizontal axis is M or N, and then the lines vertical are also values of M or N. M or N are interchangeable. So I went into M equals 0.5 and N equals 1, or M equals 1 and N equals 0.5, I would get the same result. The result I got for this first example was 0.12. So my change in vertical stress underneath the corner of this area is 0.12 times 1,000 is 122 PSF. The change in stress underneath the edge of this one is, say if I want to go to the middle of the edge, I divide this into a couple of rectangles. Because remember, my table or my chart is only underneath the corner of a loaded area. So underneath the corner of the loaded area, 3 feet by 3 feet, I get one rectangle, Z equals 6 feet, M is B over Z is 3 over 6 is 0.5, N is L over Z is 3 over 6 is 0.5. I go to the chart and find the influence value of 0.084. So my increase in stress for this scenario is going to be 2 times 0.84, 2 times 0.084 times 1,000, because each one of these has 0.084, and I get 168 PSF. So again, my general solution on that chart is for underneath the corner of the rectangular loaded area. Okay, if I had this one where I had underneath a point that wasn't underneath the center of the edge, just some arbitrary point, I can still divide it into 2 rectangles. It just wouldn't be the same. So I would end up with 2 rectangles, rectangle 1 and rectangle 2. One is 4 by 3, the other one is 2 by 3. I calculate my M and N for the 2 by 3, 2 over 6 and 3 over 6, and then M and N for the 4 by 3 is 0.5 and 0.67. I get a value for I for the 2 by 3, which was 0.061. For the 4 by 3 is 0.1. And add those two together and multiply by 1,000 and get 161 PSF. The last example with this set is, what if I had this case while underneath the center of this area? Then I need to divide it into 4 equal rectangles. So if you look at this picture here, I divide it up into 4, then do 3 by 1.5. So 3 by so M is 1.5 over 6, N is 3 over 6, and I get an I value of 0.048 times 1,000 is 192 PSF. So I've got to multiply that by 4 because I've got 4 of these equal rectangles together. So you begin to see through those very simple examples how you can use all 4 of those together or how you use that rectangular chart, and you can use it for very versatile situations. That's why it's a pretty popular method for calculating stress change. The other thing I want to talk about stresses today is, in addition to stress changes, let's talk a little bit about just stress in general at a point. Now, what we talked about so far is just the normal stress. Let's talk a little bit about normal stress and shear stress, and this is kind of a little bit of a review of solid mechanics, enough that you can understand some of what's happening with stresses in a soil mass, and then we get to talking about strength later. So if you look at normal stress in 2 dimensions, we'd have, a vertical stress I'll call sigma z, and the horizontal stresses I'll call sigma x. And geotechnically, we're typically looking at compressions that are pushing inward. And then also on the planes, we may have combinations of shear, a couple of shear couples. So tau zx and then tau xz on the verticals. So we have some combination of normal line shear stress on the face of the element. Now, you probably all remember seeing Mohr circle of stress, but just to remind us that if I cut planes in any arbitrary direction through a point, then I could have any combination, almost an infinite combination of stress combinations of normal and shear, depending on which plane that I cut through. And Mohr circle of stress gives us a way of showing all those combinations in a very simple diagram. And it gives us a powerful computational tool that we can use to calculate stress on planes that we don't know about or we want to find out the stress on. So a Mohr circle of stress, very simply, is if we know the stress on two planes, we can plot these two planes on a Mohr diagram and then draw the Mohr circle center. And the center is always on the horizontal axis, always on the stress axis. So Mohr circle is in what I call tau sigma space, where we have shear stress on the vertical, normal stress on the horizontal, and these axes are in equal dimension. So they have to be in equal dimension, otherwise this doesn't become Mohr circle, it becomes an egg or oval or something like that. So we plot them in equal dimension. And a couple of very important things to note about a Mohr circle are this. The top of the Mohr circle and the bottom of the Mohr circle is the maximum shear stress, and that's the plane in which they act on. And if we're talking about shear and stress in the soil, that can become very important. Where's all the shear, the maximum shear. Another thing is planes where there is no shear stress are called the principal planes. The major principal being the larger value and the minor principal being the smaller value. And usually in geotechnical problems, these are going to be the vertical and horizontal planes. Structural engineers might come up with something crazy based on their design, but most of our geotechnical problems have nice vertical and horizontal principal planes. And that works to our advantage when we're calculating stresses later. So just a quick example to plot is I'm going to say that I know the normal and shear stress on a couple of planes. I want to plot a Mohr circle and look at the plane, calculate stresses on the plane, which is 30 degrees clockwise from the horizontal, and then locate the major and minor planes relative to the horizontal. This is, I'm not expecting you to get all this, but I just want you to kind of see the use of the Mohr circle right now and you can identify the principal planes. Here are the two planes, 1400 PSF vertical with 450 shear, and then another minus 400. I'm putting attention on this example with a minus 450 PSF shear. I drew this as an element, which makes more sense. The vertical stress being 1400 in compression, horizontal stress being minus 400 in tension, and here my shear stress is 450 on this plane. If I plotted Mohr circle like this, it would look about like this. These two planes, the vertical and horizontal, were separated by 90 degrees. In Mohr circle space, that's 180 degrees. So 1400, 450 on the horizontal plane, and working my way over to the vertical plane is minus 400 and 450. This is the vertical plane, and then going over 180 degrees in Mohr circle is 9 degrees in reality, and that's 1400 and 450. My major principal plane then, so once I establish those 2 points, I can plot my circle. I plotted the circle. Now I can find my major principal plane and my minor principal plane, and then also look at the that other plane I was talking about. So if I wanted to find 30 degrees, a plane that's 30 degrees from the horizontal plane, that was where the 60 degrees comes from. And 30 degrees from the horizontal plane is 1340 and minus 550. The major and minor principal planes are at 27 degrees here and 153 degrees this direction from the horizontal plane. So this is more or less what I have drawn in here. So the major principal plane is 13.5 degrees clockwise from the horizontal, which is 27 over 2, and the minor is 76.5, which is 153 degrees over 2. And again, I didn't say it directly, but in the real world versus Mohr circle has a double angle. So if the real world it was 9 degrees apart, and Mohr circle would be 180 degrees apart. But at the end of the day, just remembering that we may be looking for these principal stresses. These are going to show up again later if we get the shear strength. And and it'd be important to remember where the normal stresses would come from. I don't know if how much longer we want to keep going. I know we're a little over time. Sarah, you can chime in here. This could be an opportunity to either skip a little bit of material, or we could kind of break and maybe push this off to the next topic. Need some feedback here. What do you think?
We probably don't want to go too much longer. I know we started a few minutes late, but I don't know if there's the opportunity to shuffle a little bit to next session. I mean, we could go a few more minutes, but because this is an opportunity to break, then I'll leave that up. I don't want to go too much longer than what we communicated.
Why don't we go ahead and stop here, because I think I could shuffle a little bit, and then we could start with a couple of the other topics and pick up next time.
Okay, great. Let's see. All right, well, Brian, do you want to say anything else before we end this first session, or?
I just want to thank everybody for listening. I know we went fast, but my intention again was to try to remind you of hopefully some things that you saw a few years ago or many years ago in Soils 1, and we're still going to work with Robert, and hopefully we can cover the rest of these topics at the beginning of the next session. So thanks for your attention. I appreciate working with you guys.
Okay.